Hello, everybody. Welcome to your next video in this probability series of videos. Topic for this video today is conditional probability. So up to this point, we've only been dealing with probability events that are separate. We were trying to find and probabilities or probabilities. This is a slightly different idea called conditional probability, where I'm going to give you a condition that you must meet before you calculate the probability. If we were in class, I would have you do this first problem on your own, but I'm going to help you with it, obviously, because we're sitting here. This is just a good review of two-way tables and how to calculate and find probabilities in a two-way table. So let's look at this first question. We're talking about, for the next couple of questions here, to introduce conditional probability. These are, we're talking about birds or crane types. So cranes are those like really tall birds that have really big wings. Typically they have like long necks and stuff. So we're talking about these three different types of cranes and if they're male or female. So if you remember back to the video with Miss L, in order to figure out probabilities in a two-way table, you have to know what the totals are in all of the categories first. So I'm going to fill that in first. So remember, to find a total here, right, for like the gray crown, you have to add across. So 16 plus 13 is 29. For white-naped, I need to again add across. This is 31. And then for the Stanley cranes, it's 11 plus 19, which is 30. And then I can check to make sure I added those correctly by saying, okay, if I do 29 plus 31 plus 30, I get 90, which is what I'm supposed to get, which is the total for the whole table, right? We also have to do that for the columns, so the male column and the female column. So if I add these three numbers together, I get 44. And then if I add these three numbers for the females, I get 46. And again, just to check my math, okay, if I do 44 plus 46, I get 90, which is what I'm supposed to do. So let's answer these three other questions here. So we did part A, check, which was to enter the totals. So this next question asks, how many cranes are female? Okay, so I need to go to the female column and go all the way down to the bottom. So the total there is 46. There are 46 female cranes. Okay. Next, I need to figure out how many cranes are female and Stanley cranes. So remember that this word and means it has to be both. So the easiest way, I think, to look at an and probability is to say, all right, I'm looking at the females, which are right here, and then the Stanley cranes are right here. And the and probability is simply where those overlap. And the number that they overlap at is 19. So there are 19 cranes that are both female and Stanley cranes. So up to this point, those are things that you should already know how to do if you watched the video that Miss L made on two-way tables. This one, though, part D, is a little bit different. Okay, so this says, out of all of the female cranes. That's my qualifier. I need to do some erasing. Sorry, that line was terrible. Okay, so out of all of the female cranes, I need to also do some erasing right here. Sorry, I'll go back and add those in a minute. But this says, out of all of the female cranes, what is the probability that we get a Stanley crane? So this problem gave you a condition that you had to satisfy. It said, I don't really care about the male cranes. I only care about the female category. That's it. So in the female category, right, I have 13 gray crown cranes, 14 white-naped, and 19 Stanley cranes. So the question is, what's the probability that I get a Stanley crane? Well, so there's 19 of them total, but then the question is, okay, what number do I put on the bottom? Since I don't care about the male cranes in this problem, right, I'm going to like cross them out. I don't really care about these. I only care about the female cranes. So what that means is when I put the total on the bottom, it's not going to be the total in the whole table. It's just the total in this category, which is 46. So what you just did here, or what we just did here, is called a conditional probability. I gave you a condition, right, or a restriction, and then we found a probability just within that category instead of within the whole group, okay? So if you look on the left side of your screen, I give you an actual definition of conditional probability, okay? So conditional probability is the chance that one event happens given that we already know another event has happened. So in that last problem, the thing that already happened, or the qualifier that I gave you, was that the cranes that I'm looking at had to be female. That's the thing that we already know has happened. And then I want to know, okay, if I'm looking at just the female cranes, then what's the probability in that category that I pull a Stanley crane? Okay. The word that is associated with conditional probability is the word given. Most of the time, you're going to see the word given in these problems, okay? Or they will give you a qualifier like I did, okay? The symbol for given is a line, okay? So this right here, that means it literally translates in English to the word given. So this is the probability of A given that B already happened. Okay. The way that you calculate a conditional probability is exactly the way that we calculated it in part D of that first problem. So we found A and B, so what they had in common, which was 19. Okay. We found A and B, and then we're dividing it. Instead of dividing it by the total, you're dividing it by the total in the category, right? Or the probability of that category. Okay, so I'm going to label this a little differently for you here. Okay, so this right here is the two events together. Okay, and then on the bottom, this is the number or the probability of the restriction. Right? Or you'll hear me call it the restrictor category. Okay. What this does is it allows me to say, okay, I'm getting rid of everything else. I only care about what's happening in this category. Right? So that's what goes on the bottom. Okay. So let's try and calculate a couple of these given probabilities here. Okay. So one of the most important things to figure out when you're doing given probabilities is which category is the restrictor category, because that's going to change what goes on the bottom of your fraction, right? The number or the probability. If they give you probabilities in the problem, like in a Venn diagram, for example, you would put a probability on the bottom. But in two-way tables, most of the time they're going to give you numbers, right? So the number in that category goes on the bottom. Okay. So let's take a look at number 2 right here. Okay, so same table, and the question is, what's the probability that a crane is male given that it is gray crowned? Okay, so the way I would write that is probability of male given, so that's my line right there, means given that it's gray crowned. Okay, so the restrictor category always comes second, always, always, always. Okay, so if I go back up to my table, I gotta change colors here. If I go back up to my table, I'm saying, okay, gray crowned. Actually, let me do some erasing here so that you all can actually see what's happening. I'm gonna have to do a lot of erasing in this video, I think. Okay, so this one was 44 and this one was 46. Okay, so in part A here, I'm saying, okay, I only care about this category, the gray crown category. And I actually recommend that you go and circle these when you're first learning them because it makes it a little bit easier to do. Okay, so I'm saying, okay, male given gray. So I only care about these. So that means the number on the bottom has to be 29 because it's the total in that gray crown category. Okay, and then I want how many males are there in that category. Right, and the males were right here. So 16 goes on the top there. Okay. All right, so that's how you calculate a conditional probability. Ooh. Sorry, this is doing some weirdness. Okay, the second part says, okay, let's switch it now. So this is what's the probability that I get a gray crown crane given that it's male. So it's the same two categories, but I'm going to switch them. So what's the probability that I get a gray crown crane given that I already know that it's male? Okay. So what that means is my restrictor category changed, right? So instead of saying this is my restrictor category, I'm saying male is my restrictor category this time. So 44 is the total in that category. So that's what goes on the bottom. And then still what they have in common is still that 16. So see, the numerator didn't change, but the denominator changed because I switched the order, right? And I gave you a different restriction. So it's really, really, really important that you know which category is your restrictor category because otherwise you will get the problem wrong. Okay, I'm kind of running out of room on my page here, but let's look at this last one. So the last one is the probability that a randomly selected white-naped crane is female. Okay, so this one is a little bit harder to figure out what the restriction is. Okay, but I'm finding the probability that a white-naped crane is female. So the condition or the restriction is the white-naped crane. So I'm finding the probability that I get a female given that I already know the crane is white-naped. Okay, so my total for, and I'm going to switch my colors one more time here. Let's try like a purple. Okay, so my restrictor category is this one, the white-naped. So the number that goes on the bottom is 31 because that's a total in the white-naped category. And then I'm saying, okay, well, how many females are there inside that category? And there are 14 females inside that category. All right. So I'm going to give you all a couple of minutes, right? So pause the video for me and I want you to try number 3 and then come back and we'll check on it. So you have to fill in the totals and then calculate your conditional probabilities, right? See you in just a second. Pause the video, try number 3, and then come back and we'll check those. All right, welcome back. So if you take a look, I completed those 4 parts of this problem. So check your answers against mine. So for part A, this was probability of 5 or more given that they were in 9th grade. So 9th grade was my restrictor category. And then I had my, there's 8 people within that category that paid $5 or more. Then I did a similar thing for 10th grade, 11th, and 12th grade. Okay, so 9 out of 19 for 10th grade, 17 out of 26 for 11th grade, and then 11 out of 14 for 12th grade. So the reason that we use conditional probabilities is to see the differences that may occur in probabilities across different categories, right? So like we can see obviously that the seniors paid a lot more proportionally than or donated a lot more than maybe say the ninth or 10th graders, right? The ninth graders were at less than half, so were the 10th graders, and then the proportions increased as you went up the grade scale. So that's something that that we use conditional probabilities for. It's makes it a lot easier for us to do fair comparisons between things because we're comparing or calculating probabilities just within the individual categories. Okay. So that's how you do conditional probabilities with two-way tables. You can also do them with Venn diagrams. So I'm going to tell you a little bit about that. We calculate the probabilities pretty much the same way. So this will be a good review of Venn diagrams for you. And then I'll show you how we would do conditional probabilities with Venn diagrams. So give me a sec to change my slides and erase my screen, and I'll see you in just a moment. All right, so I am on the next page here, and we're going to talk about how we do conditional probabilities with Venn diagrams. So just a review for you about Venn diagrams. Typically, you're going to have two values or two categories. Okay, the number that occurs here in the middle is the number that fit in both of those categories. The numbers that occur outside, typically there's a box around them, are the total in the whole circle. So see, if I do 20 plus 4, I get 24. 37 plus 20, I get 57. Okay. The numbers that are in the kind of moon-shaped parts of the circles are the number of people or things that fit only in that category and not in the other one. So here, for example, my two categories are tortoises and then known gender. So there are 4 tortoises or 4 animals that are tortoises, but we don't know their gender. Okay. And then the number in the bottom right-hand corner is the number that fit, or the probability that fit in neither of those categories. So there's 30 animals that are not tortoises, and we also don't know their gender. Okay, so let's answer some of these questions about our Venn diagram here. So the first question is, how many animals are there at this location? So if you want the total, remember you want to add, or the total in the population, you add all of the numbers that are inside the Venn diagram. So not the ones that are outside, not the 24 and the 57. We're going to add these 4 numbers right here. Okay, so 20 plus 4 plus 37 plus 30. Okay, and give me just a sec because I have not done that one yet. Whoops. Okay, so if I add all of those numbers up, I get 91. Whoops, sorry, getting a phone call. Okay, so I have, sorry everybody, this keeps flipping back and forth. This is what happens when you get calls from telemarketers. Okay, so 91 total animals here. Another way that you could figure that out is you could add these two values, the totals in each circle, subtract what they have in common, and then, but you have to remember to add the number that fit in none or neither of the categories. It's important. Okay, don't want to forget about them. Okay, so part B says, how many of the animals are tortoises? So that question is not how many are just tortoises, but how many total are tortoises. So that's this number on the outside. So 24. Okay. Part C says, how many animals are of known gender? So again, not just of known gender, but total known gender. So that's, again, the number on the outside, which is 57. Okay. And then part D says how many of the animals of known gender are tortoises. Okay. And this one is a little bit confusing the way that it's worded, but what they want you to tell them is how many animals fit into both of those categories. So that's this guy, the intersection in the middle. So that's 20. Okay. Now here comes the conditional probability part. Okay, so the first thing they want us to calculate is K given T. Okay, so this T is my restrictor category. Okay, so what that means is it's very similar to the way that we did in the two-way table. If T is my restrictor category, then I'm going to circle that and say that's the only one that I care about. Okay, so that means my total or my denominator of my fraction will be the total in that category. Okay, so 24. And then I want K at the top. I want, okay, how many of those that are in the tortoise category are also in the K category? And that's 20. There's 20 of them. So that's the intersection of the Venn diagram. Okay, right? So remember, going back to our definition, right? The definition of a given probability is A and B divided by B, right? So 20 is the intersection of these two things, T and K, divided by T, the restrictor category, okay? Second example here, we're going to switch them this time. So now I'm saying that K is my restrictor category. So I'm going to go ahead and circle that and say K is my restrictor category. So that goes on the bottom. So the total in my restrictor category now is 57. But the intersection, right, what they have in common, so how many of the K animals also fit in the T category is still 20. Okay, so in both of these examples, the numerator is the same, and they represent the same place on the Venn diagram. Okay, which is what this last question is do they represent the same region? Yes, they do represent the same region, but the probabilities are different, right? And the reason that they're different is because we're dividing by a different total, right? The restrictor category is going to affect what our probabilities are, all right? So I would love for you to try the last problem there, number 5, on conditional probability, but with Venn diagrams. But this time we're dealing with probabilities inside the Venn diagram instead of numbers, okay? But keep in mind, the actual dividing and all of that stuff is still the same. The definition of conditional probability is still the same, okay? So like down here, this, the 0.27, is still that's the probability of T and N together. Okay. So give me a second to erase my screen and pull this down so that we can see these problems a little better. But like I said, I would love for you to try it. So pause the video, try those, the parts of that problem out, and then check it with me. I'll be right back. All right, here we go on our last problem. I'm hoping that you did these on your own. So check your answers against mine. So part A says, and in this problem, we're dealing with this whole box is like monkeys, right? Like types of primates or a number of primates. T represents a tamarin monkey, and then N is the event that the primate is, what is it? At least 9 years old. Okay. So the very first part here, part A, says, what's the probability that a randomly selected primate is a tamarin and is at least 9 years old? So the probability notation is T and N. So remember, and is simply the intersection right there. So you didn't have to do any math at all. You had the answer already. That value is 0.27. Okay, what's great about Venn diagrams that have probabilities in them is sometimes you don't have to calculate anything. You can just read the probability directly from the Venn diagram. Whereas in the others, we've had to write fractions, right? Like with the two-way tables and with that last example that I did with the different Venn diagram that had numbers in it, okay? Part B then says, what's the probability that a randomly selected primate is at least 9 years old? So I just care about what's the probability that I get a 9-year-old primate. So remember, 9 years old is this entire circle right here. So it's not just the 0.21, it's the 0.21 and the 0.27 together. So I'm going to add those. So 0.27 plus 0.21, which is 0.48. Okay. And then my last one is, what's the probability that a randomly selected primate is a tamarin given that it is at least 9 years old? So that's T given N. And I'm going to write the probability out like with the definition so that you can kind of see what this looks like. So remember, it's the and probability. Oh, whoops. Oh dear, I erased my whole screen by accident. Give me 1 second. I have to rewrite these. Okay, we're back. Sorry about that. So in this last problem right here, like I said, we're finding a conditional probability of a tamarin given that it was already 9 years old. So I'm going to go back, like I said, to our definition, and I'm going to try not to erase my entire screen this time. Remember that conditional probability is the and probability of those things, so T and N, divided by the restrictor category, which in this case is N. Remember, it's always going to be the second category that's listed there. It'll be after the given, always. So you have both of these probabilities already, right? Probability of T and N you have up here, and then the probability of N you have right here. So let's just plug those values in. So I get 0.27 on the top divided by 0.48 at the bottom. Okay, so this is probably going to look a little bit weird to you because you have decimals inside of a fraction, but you can just go ahead and divide those and get a different fraction. So when you do 0.27 divided by 0.48 in your calculator, you get 0.5625. Okay. So in all the previous examples that we've done, in the fractions, there have been numbers because that's what we've had. Like it would be the number of T and N and the number of N. But in this Venn diagram, we have probabilities. But the process is exactly the same. The location that you're looking at is exactly the same. The only difference is that they're represented as actual probabilities and decimals instead of as numbers. Okay? So that is it for conditional probability. We're going to use this idea in the next lesson when I talk about independence and the multiplication rule. So I will see you in the next one. Bye.